Hello guys, and welcome to my YouTube channel. In this video I am going to explain DC and AC differences and their use cases. So how exactly do you choose between AC and DC? It's the fundamental design question you'll face everywhere, from microelectronics all the way to macro grid infrastructure. And here's the thing, it's not actually a matter of one being inherently better than the other. No way. It's entirely about picking the form of electricity that minimizes your loss, your conversion costs, and your system complexity for the specific job at hand. To figure this out, we're going to break this decision matrix down into 5 quick steps. We'll define the waveforms, master AC behaviors, match our sources to our loads, calculate long-distance grid costs, and wrap up with the hybrid future. Alright, step 1, defining the waveforms. We really need to ground ourselves in the basic physical properties of our currents here. The whole foundation of our decision really starts right here. DC, or direct current, keeps a totally steady direction, where polarity definitely matters. Think of a battery hooked up to an LED. The voltage and current are constant. But then you have AC, or alternating current. This introduces a reversing sinusoidal waveform. So in an AC system, like plugging a space heater into a wall outlet, the voltage actually crosses zero and reverses direction every single half cycle, usually running at 50 or 60 Hertz. Because it's constantly fluctuating, we rely on RMS, or root mean square values, to actually link that reversing voltage and current to a really useful equivalent heating power. Moving right along to step 2, mastering AC behaviors. Let's look at how this builds into complex circuit behaviors. Mostly because AC introduces frequency, phase, and impedance to the mix. Now, this is where things get super interesting. Because of that frequency, we're no longer just dealing with simple resistance. We are dealing with impedance, the combined effect of resistors, inductors, and capacitors. Notice how inductors and capacitors actually store and release energy every single cycle. They're constantly charging and discharging, which causes power to just slosh back and forth without doing any useful work. We call this reactive power. Think of it kind of like the useless foam at the top of a glass of root beer. You can't drink the foam, right? Managing your power factor, basically the ratio of real working power to that useless foam, is a massive part of AC engineering. It's wild to see how the exact same components fundamentally change their behavior when you shift from a DC steady state to an AC frequency. Take a charged capacitor, for example. In a DC circuit, it completely blocks steady current. Done. But hit it with AC, that constantly changing voltage means the capacitor is always charging and discharging, so it effectively passes the current right through. Inductors do the exact opposite. An inductor acts just like a short circuit in steady DC, but it aggressively opposes changing AC current, creating high impedance. This little behavioral flip, that's literally the secret sauce behind transformers and induction motors. Okay, step 3, match source and load. Armed with all that theory, this is where we actually start making practical design choices by looking at the physical requirements of our system. Every single engineering choice you make is going to start with 4 crucial procedural questions. This helps you figure out if a fixed polarity or easy voltage transformation is your top priority. 1. What's generating the power? Are we talking about a spinning turbine or a solar panel? 2. What does the end device actually need to function? 3. How far does this power have to travel? And 4, what kind of power electronics or transformers are we actually willing to pay for to convert it? Let's apply those questions to some real-life examples. If your system involves storage, semiconductors, or needs controlled polarity, like an EV battery pack, your smartphone, or say an industrial electroplating facility, DC absolutely dominates. Those loads just fundamentally need a fixed polarity to work. But if you're running heavy machinery, I'm talking massive induction motors, the compressor in your HVAC unit, or the elevators in a skyscraper, for those, AC is your absolute workhorse. The reversing magnetic fields and 3-phase AC power are just incredibly efficient at driving smooth, powerful rotation. Which brings us to step 4, long-distance grid costs. Let's zoom way out to the macro level and calculate the physical and economic realities of moving all this power across entire continents. So AC distribution is the heavyweight champion, the default for interconnected grids. Why? Simply because transformers make it unbelievably easy to step voltage way up for long-distance transmission and then back down for local neighborhoods. The catch is, transformers only work with changing magnetic flux. That means they require AC. They literally do not work with steady DC. Being able to use these rugged, super simple transformers lets us easily match voltage levels from a distant power plant, across the state, straight to your kitchen. But hold on, Why do we even need to step the voltage up in the first place? Well, it comes down to the math, and it's kind of mind-blowing. If you try to transmit 1 megawatt of power at just 1 kilovolt, you're going to waste 500 kilowatts to I squared R heating losses. Half of it, just gone. But if you step that voltage up to 100 kilovolts, that loss drops to a mere 50 watts. I mean, let that sink in for a second. For the exact same amount of delivered power, jacking up the voltage lets you drastically drop the current. And since wire heating losses scale with the square of the current, dropping the current is absolutely crucial for grid efficiency. Pushing power at 1 kilovolt gives you unacceptable losses, but stepping it up to 100 kilovolts, which AC does so cheaply, basically cuts that loss to almost nothing. Now, AC makes this massive infrastructure possible. Just think about the sheer scale of those high voltage transmission towers you see on road trips. They're everywhere. But modern engineering is actually finding scenarios where AC isn't the most efficient answer for massive distances. While three-phase AC is great at sharing power smoothly, once you get into incredibly long distances or super specific geographic challenges, the actual physics of AC start working against us. And that's exactly why, as noted by groups like NREL, HVDC or high voltage direct current is stepping in for some very specific use cases. We're talking undersea cables and connecting grids that aren't synchronized. Remember how we just talked about capacitors and AC circuits constantly charging and discharging? Well, a long undersea power cable is basically just a giant, miles-long capacitor. If you pump AC through it, you lose a ton of energy just dealing with that charging current. HVDC avoids this entire headache because steady DC doesn't trigger that capacitive charging. Plus, it has lower right-of-way needs and can seamlessly link two different AC grids together, giving us massive loss reduction over those really extreme distances. That brings us to step 5, the hybrid future. Because the future of engineering isn't really about choosing just one, it's about seamlessly integrating both. Thanks to incredible advances in power electronics, engineers can now use the absolute best form of electricity at every single stage. Think about it, solar panels naturally generate DC. Our macro grid is mostly AC, and our electric vehicles store DC in their batteries. Modern engineering relies on rectifiers to turn AC into DC, and inverters to flip DC right back into AC. We are no longer locked into just one standard everywhere. We can use the heavy lifting, easy stepping power of AC for bulk distribution, and then use smart power electronics to create hyper-efficient DC zones exactly where the energy is consumed or stored. So ultimately, your job as an engineer is to balance those physics and economics. Will you lean on the robust transformation of an AC network, or maybe the precise, storage-friendly stability of DC? As power electronics get more and more advanced, it really begs a provocative question. Are the massive, sprawling AC grids of today eventually going to become obsolete, replaced entirely by hyper-efficient DC microgrids? As you step up to design the electrified world of tomorrow, how are you going to bridge the gap? Thanks for watching this video, guys. Please share, like, and comment below. Also subscribe to my YouTube channel for more videos.